Thank you, ma'am, for that nice introduction. And I would also like to thank the organizers for giving me this opportunity to connect with teachers from all across the country. Very interesting statistics you were reading out, Mr. Harish. So I think it's a privilege to be connecting with you. And during the course of next 40-45 minutes, I'll just take you through India's journey in the area of human spaceflight. Of course, there are challenges. We are still in the process of achieving our own human spaceflight mission, but it also brings forward so many opportunities for not just for the Indian community, the space community, but also for many other scientists because it opens up new arenas for us where we move from generic space activities to human spaceflight activities. So with that, I will start my presentation. I'll just start with a few questions because we have all the teachers here and teachers love to ask questions. So I think we should all think about these questions. First of all, what fascinates you about space? So what fascinates one about space is its vastness, its openness, the fact that it is so full of opportunities for humanity to explore, to go beyond all the frontiers. And where does space begin? It's a very difficult question to answer, even though there is a commonly agreed line called as the von Karman line, which is at an altitude of 100 kilometers. But still, there is a lot of discussion going on in UN forums on space, and it is still not fixed. It's not. There is no common sort of barrier that is agreed as space. But the legal processes apply differently to airspace and space as such. Now, do you think life is possible outside our planet Earth? Well, even today, it is only a very small probabilistic kind of possibility that we see, and there is no proven record to say that there is life beyond Earth. And just to give you a feel of how fast does the space station travel, well, it's around 28,000 kilometers per hour. The astronauts need to wear spacesuits because it is more or less like their room in which they have all that is required for them. What would happen if you pour water into space? So many of you would have seen these videos being telecast from the space station where you see water droplets being flying around. But that is still inside the space station where you actually have air, where there is an atmosphere created just like Earth's atmosphere. But if it were to pour into space, it will just evaporate within no time because of the vacuum that is there, even at room temperature. What protects Earth from meteorites and radiation from the sun? Of course, it's our atmosphere. There is a Van Allen belt where the radiation levels are higher, and that is close to South Pole. So that is a very high radiation-prone area. Then there are questions like, what do pilots and astronauts have in common? Well, actually, they do not have a lot in common. There are a lot of differences in terms of approaches when we compare pilots and astronauts. So with these few questions, I will just take you through this presentation. Just to give you an overall idea about how global human spaceflight scenario looks like. Well, as of today, there are just 3 countries which have the capability of an end-to-end human spaceflight, and that is the USA, then erstwhile USSR or Russia, and of late China. So if we demonstrate human spaceflight capability, we will be the 4th country in the world to do so. And all these countries, they have all focused on the low Earth orbit, which is at an altitude of around 400 kilometers. But US is only the one which has been able to reach moon or the lunar surface. Of course, they have had space stations, but that is also in low Earth orbit. So Russia and US had space station, and then there is an international space station which is of a consortium of countries. And recently there is a Chinese space station by name Tiangong. So these are the space stations in orbit. And if you follow how the space activities have been progressing, you will notice a very common, very visible trend that there is a renewed interest in space exploration lately in the last, let's say, 5 or 7 years or so. And the reasons for that is one, of course, all these private industries coming into play. So earlier on, it all used to be government agencies run space programs, but now there are business opportunities for the private sector. So people are looking to revolutionize the whole sector. They're looking to optimize things. They are looking to come up with innovative ideas. So companies like Axiom Space, SpaceX, Boeing, Blue Origin, they are all looking at different sort of objectives for their space program. And now people are actually looking beyond the International Space Station. They're looking at having robotic missions to complement human missions in space exploration. And there is an ever increasing risk posed by these sort of initiatives. Of course, people are talking about building habitat on moon, going to asteroids, exploiting resources, space tourism, and things like that, which I'll briefly touch upon during my presentation. Now, as far as India is concerned, there has only been one Indian in space, and that is Wing Commander Rakesh Sharma, who went to space as part of the Intercosmos program. And we are very closely in touch with Rakesh Sharma sir during our entire program. He is a member of several of our committees, and he regularly visits the center. It's always a pleasure to interact with him, and it's always a learning experience too. So he went on Salute 7 mission in 1984, and the duration of his mission was 7 days, 21 hours. Of course, he underwent all, for the first time in Indian getting astronaut selection, training experience, space flight experience. He did certain experiments on board. He did yoga for mitigating space flight hazards. Some of our labs were developed for space food development. So there were many takeaways from this mission, I would say. But more importantly, he has and still is served as a role model to you, to all of us in one way or the other. And he has been an inspiration for space exploration. Of course, there is a larger angle. When last December, the NASA administrator was here, he made it a point that he has one-to-one lunch with Rakesh Sharma sir. So, a person like him, it helps in strengthening of international relations too. So there are many different angles to an astronaut going to space. As far as India is concerned, we have been pursuing this idea of a human space flight for almost 2 decades now. And there were several technologies that were required to be accomplished. So the space capsule recovery experiment in 2007, we were able to demonstrate re-entry to atmosphere after going to orbit. And we qualified certain materials, the thermal protection system materials, due to this mission. We enhanced the capability of our launch vehicle that was required to take a human capsule. So the GSLV Mark III achieved a 10-ton capacity to low Earth orbit. And various other parachutes, the crew escape systems, they were developed through the pad abort test and care mission. So it was around this time, around 2018-19 period, where we could go back to the government and, with a lot of conviction that we were now there, we had the basic technological elements that were required to take up such a challenging mission, and we were able to convince the government. So this was approved by the government in December 2018, notably as a national endeavor. So it was not just a mission of Department of Space, but many institutes, many agencies, many departments became a part of this. And the approval was for a sustained and affordable human and robotic program to explore the solar system and beyond. Of course, starting with the solar system and demonstrating human space flight capability to low Earth orbit. And here we're looking at a crew of, let's say, 1 to 3, maximum 3, for a duration ranging from 1 orbital period to going up to 3 days, along with conducting some microgravity experiments. And there will be at least 2 unmanned developmental missions prior to demonstrating the human spaceflight. So this is the vision for the Gaganyaan program. This is the configuration. The launch vehicle that will be used will be the launch vehicle Mark III, the human-rated version of launch vehicle Mark III. So in terms of propulsion systems, it capitalizes on all the experience that ISRO has developed over the years. So it has solid propulsion in the form of the S-200 strap-on rockets. Then it has the liquid stage as the core L-110 stage, and it has the indigenous cryogenic stage C-25, which is now upgraded to C-32. And then you have the orbital module, which will be orbiting at an altitude of 400 kilometers. And there is a crew escape system attached at the top of it to, during the launch phase, if there are any off-nominal situations, the crew can be taken to a safe distance within a very short time. The orbit that we are aiming at is 400 kilometers circular at an inclination of 51.5 degrees. So this is more or less similar to the orbit of International Space Station. The orbital module has two parts: the crew module, which will of course be the habitat for the crew, and you can see the crew in reclining position, and you will ask why that position. So it has got a lot to do with the kind of loads that the crew experiences during space flight, the kind of acceleration levels that he experiences. The human body is capable of withstanding these loads in a particular direction, and the capability changes with the orientation. So, for example, if the loads are coming normal to the chest, you have a higher capability. But if it is along the spine, you have capability to take on only very few G loads. So those are the kind of points that go into the design of such a module. We are expecting it to land after completion of mission in the sea. So we're planning for recovery in the sea on both sides of the country. Primary site is in Bay of Bengal, close to Andaman and Nicobar Islands, and the secondary site is in Arabian Sea. Now, for ISRO, there is it's a paradigm shift going from space to human space, because entire philosophy, entire thought process, the procedures of qualifying systems, everything changes for us. So we move from a performance-driven approach to a human-centric approach. Now it's not about optimizing the performances, but crew safety gets paramount importance. It's no more just restricted to systems reliability, but human rating becomes important. So there are higher levels of margins of safety, more redundancies in the system, contingencies plan, and automated health monitoring system. So all these form part of the human rating. And unlike our satellites, where the focus is always on carrying certain payloads, like the communication payloads or Earth observation payloads or navigation satellites, the focus is now on experiments. And these experiments, they just don't restrict themselves to engineering, but there's a lot that we can do in science. There's a lot that you can do on health, medicine, pharmaceuticals, chemicals, and things like that. And of course, there is a crew escape system for contingency. So just to give you a very simplistic representation of how we execute this whole program, there is a high priority on crew safety. We go in a step-by-step approach with extensive qualification and functional tests. So it's many times higher than an ordinary mission. So you go for a huge number of qualification tests, functional tests, simulations, and then we don't stop at that. We also qualify all these things on simulated flight platforms, like certain parachutes and crew escape systems. You qualify with the help of helicopters, aircraft, some small stage rockets which can go to something like intermediate altitudes, and then you go to the uncrewed mission, finally going to the crewed mission. And during this process, the human flight certification also takes place. Now, one major milestone we achieved was in last October, when we carried out the test vehicle T1 mission. And in this mission, we designed one particular test vehicle for carrying the entire crew escape system to something like 17 kilometers altitude. And then the crew module got separated from the test vehicle, it reoriented itself, and all the parachutes, starting from the apex cover separation parachutes, the drogue parachutes, the pilot parachutes, and the main parachutes, they were deployed in that particular sequence in which it will be done in the actual mission. And the crew module splashed down close to Sriharikota. And herein, we could predict at what distance this will be falling down and at what velocity it will be falling down, and we could match those predictions. So it was within a range of 10 kilometers, and the velocity of touchdown was close to 8.5 meters per second as predicted. So all the performances, including the stages, the parachute system, were normal, and the post-flight analysis has been completed. The crew module has been recovered with the help of Indian Navy, and the same, we are trying to refurbish it for using it further in the pad abort test. And you can see some of the images taken for the parachutes and the recovery operations in those pictures. Now, coming to human space flight, one of the important things that we need to account for is we need to budget for life on board. So each process that we do in a day needs to be accounted for in terms of consumption as well as excretion. So you budget oxygen, food, water, hydrogen, and you see what is the net intake of all this. And all that you have to provision for their net intake as well as make arrangements or facilitate the excretion, collection of these for whatever metabolic waste, water, carbon dioxide is being excreted. And all this should match. So this is how you budget for life on board, and this is done through various systems. And the important system here is the environmental control and life support system, the aim of which is to provide an environment just like we have on Earth, called as the short sleeve environment in space. But this is not a single system. This is actually a system of systems. So this has the cabin pressure control system to maintain, air pressure, but also a percentage of oxygen, nitrogen, similar to what we have on Earth. Then you have the thermal and humidity control system to maintain temperature and humidity, air revitalization system to keep filtering the carbon dioxide that is generated. Then you have a controller to control all this with precision. You have ground servicing equipments, actually a reporter. There is an environment monitoring system consisting of many sensors. In all this, you have to have long simulations, even going beyond the mission duration to demonstrate the performance. Then there are many human-centric products and flight suits that are required, and some of them are listed here. So you have the flight suit, of course. In case of the ECLSS system not working, this serves as a backup. So you can always put on the flight suit, pressurize it, and you get some time to be in orbit longer and enable you to abort the mission and come back safely. So it gives you that much time. Then there are emergency survival kit, which has food kit, hygiene kits, medical kits, and all these are being developed indigenously, apart from the flight suit. Then the fire suppression system, you have the emergency survival kit, then you have a crew seat, which provides comfort to the crew and which should be capable of absorbing or attenuating all the loads that come during the course of the mission. Now, what are the challenges you face in space? Well, gravity itself imposes a lot of challenges. Our human body has got adapted to gravity, over so many thousands of years of our existence on Earth, and everything, the digestive system, the circulatory system, the nervous system, it has got used to working on Earth and under the impact of Earth's gravitational field. The moment you move away from this gravitational field, many changes start occurring to your body, and I'll touch upon those. But it is not just gravity that impacts you, but the environment, the hostile, close environment itself can start impacting your mental health. The distance from Earth, when you talk about long duration missions and interplanetary missions, isolation and confinement, and then radiation poses great health hazard in space. So these are just some of the estimates. Like if you were to spend, let's say, 1 year on Earth, your dosage would be something like 4 millisieverts. But if you spend even 6 months on ISS, it will be something like 80 millisieverts, almost 20 times higher with half the period. So, and as you go further, those levels are much higher. When you go to Mars, it is 300 millisieverts. If you make a round trip of, let's say, 30 months, it can be 1000 millisieverts. So those kind of levels. Now, even the gravitational forces, when you talk about other planets, it can change, it can vary. Those will have their own impact on Earth or on the human health. So this becomes very important, and this is an emerging area of research which is called as space medicine. So here you need to understand what are the challenges and how you can mitigate them. You need to diagnose what are those conditions that are existing. So the flight surgeons need to be part of the mission. The crew medical kit has to be equipped to deal at least with some of the situations. And here we've got good amount of help from the Institute of Aerospace Medicine of Air Force, which has been training the pilots for decades, for Air Force pilots for decades. So they have got facilities for subjecting the crew to, let's say, you can see the picture. It's called as a head tilt stand. So head tilt stand produces something like microgravity conditions because the blood flow comes to your head in those conditions. So, and they have got human centrifuge. So they have facilities which can subject human beings to different conditions. Now, how does microgravity impact? Well, actually, microgravity impacts almost every part of the human body, be it muscles, be it bones, be it the feeling of nausea when you go to space. So all this, but I just touch upon some of them. Like for example, cardiovascular system. So on Earth, gravity is always exerting a downward force to keep fluids flowing to the lower body. But as you go to space, these fluids tend to redistribute. And so they move towards the chest and upper body. So this causes face congestion. And you can see some of the astronauts when they're in space, their face feels puffy and swollen. And when you come back, so what happens is your body tries to reject this excess fluid. So you tend to lose more fluid and the heart becomes smaller. And upon return to Earth, again, gravity is trying to pull you downwards. So you have this, orthostatic intolerance kind of condition. You can't stand properly for some time, let's say for a few days. So in terms of mitigation, you need to be trained for this, like CPR training of astronauts. You need to have for orthostatic intolerance, you need to have certain special garments and some salt supplementation is required. So all these are methods to mitigate. You have bone loss, so decreased bone mineral density, decreased bone strength, hypercalciuria. So you can have more chances of renal stone occurring because all this that is lost from the bones can get accumulated in the kidneys. So almost around 2% per month kind of bone loss can take place. Astronauts have complained about low back pain. The spinal size can elongate. Your spine can elongate. You can be few centimeters longer actually. So you need to mitigate them by doing exercises, and then there are nutritional countermeasures. And to train for all this, the astronauts, they have elaborate sort of training, 2 years, 3 years they carry out, and we have set up a small facility in Bangalore to assist what IAM already had. So all these hypoxia chambers, centrifuges, they have regular physical training, swimming, and all this microgravity familiarization, simulators, they get trained extensively on the simulators and mission procedures. So all this is part of preparing them for the mission. But the important point that you must note is that while the human body, when subjected to microgravity, undergoes so many changes and it impacts the human health, what experience has shown is that all these changes are not permanent and they are not irreversible. When you come back and you have your rehabilitation period, that can vary depending on the mission duration. For a small duration mission like ours, it can be 2 weeks or 3 weeks, but it can also go for long duration missions up to 3 months. After completing the rehabilitation phase, your health gets back to the stage where you were before the mission. And that's a heartening part because from the data that has been collected over the last 6 or 7 decades, there's nothing to prove that in terms of longevity, in terms of age of an astronaut, in terms of health, there is any change from a normal human being. And this has actually encouraged the space agencies to expand the envelope of human spaceflight activity. So now you see that it's not just the trained pilots that are going to space, but there are scientists, there are doctors, there are teachers, there are actors. All the people are going to space. And what does that have in store for us? So all these health aspects can also happen on Earth. So you try and relate as to what is happening and what countermeasures you give on space. Can that be also applied to Earth? And that is really working. So it is revolutionizing the whole field of medical research. And in terms of different areas that are coming up, in terms of microgravity research, you have a predictive medical model which you do for astronauts. You look at spaceflight stressors and immune response. The body tries to reject some of the microorganisms when you're in microgravity. Then you have biomedical systems modeling, human-machine interface, that's cognitive science, pharmacokinetics, how does medical behave in space, nutritional countermeasures. space motion sickness and vestibular system, radiation countermeasures. So all these become very important areas of research, and they add a lot of value to the whole medicine to health system on back on Earth. Interestingly, even the regenerative life support system is a very important thing, because for long duration missions, you've got to live with those resources that are there on board. So you try to recycle everything. And this again has a message for back on Earth, where we are fast running out of resources. So how you reduce, how you recycle, how you reuse, and how you manage the resources that you have, it becomes a very important lesson from space. Then there are scientific experiments. You conduct experiments on cells, on cell cultures, on small specimens. You do drug development, because microgravity, when you talk about multi-phase systems, you don't have this phase separation. So drug development, polymer development, even flames, the physics of how a flame propagates, all those things can be studied effectively in microgravity. And herein ISRO collaborates, in a big way with institutes, because the research is there for scientific institutions to do. We don't do all that research in-house. We just handhold the institutions. So announcement of opportunities done. We help them in developing the payloads, and then they are flown. They will be flown on some of these missions. So herein we work as a national human space enterprise, wherein ISRO, academia and research institutions, and industry, everyone contributes. Now, just to show you how ISS, as one example, has been helpful, which has been there in operation right from 2000 onwards. So this has already hosted something like 3,000 research investigations, and around 278 investigations are currently in progress on ISS. So it leads to various fields of research in biology and biotechnology. In fact, biomanufacturing, space biomanufacturing is a big and emerging upcoming area. Then you have earth and space science, educational activities, human research, physical sciences, and many technological elements. Some examples are just brought out here. So in terms of health and medicine, you look at infrared ear thermometer, artificial limb, ventricular assist device, non-invasive body imaging techniques, medicine for osteoporosis. We spoke about bone loss, advanced diagnostic tools and techniques, because here you have to manage from Earth to space. Then you talk about fire-resistant materials, firefighting equipment, and many other areas like harnessing solar energy, pollution remediation. One example is the emergency survival kit. One of the components that is there inside the kit is water desalination kit. So if there is an off-nominal landing in sea and you need to stay for more duration, there is a kit given to you where you can just fill up the seawater and add this powder and shake it up, and then all this salt and things like that settle down, and you can actually take that water. So this has a lot of implications even on Earth. But apart from this, why industries are coming into this is it brings another opportunity for exploring the world beyond Earth. As we say, everything runs out, on one particular day or the other. So people try to extract materials from different bodies in space and bring them back to Earth. There is also a possibility of harvesting on-site, which is called as in-situ resource utilization. Like you can mine ice, you can mine methane, carbon dioxide, helium, and things like that. You can collect soil to build structures, and with advent of 3D printing, additional manufacturing, and all, now it becomes a possibility. You can just go to moon and use the regolith there to construct certain habitats on the lunar surface. And people are really making plans for this. One example is some asteroids are rich in platinum. And there's one particular asteroid which is entirely made out of platinum. So people are thinking of deflecting it and bringing it down. So, and these are all costly materials. Solar energy is another thing which is there to be harnessed. So space mining is going to be a big area for the industries, and there are a lot of returns to it. Then one has to think about not just exploitation of resources, but also of making habitats in space. So we need to ask ourselves a question whether, apart from Earth, is there a plan B? So what happens to human civilization in case of a disaster, in case of a major disaster on Earth? So what do we do? already there are indications to this. We already have people in the orbit consistently for last 30 years or so. So can we make habitats which will have life support system, water recovery and waste collection in recycled way, environmental monitoring, radiation protection, and space suits meant to carry out extravehicular activities. So that becomes their dress for staying in these habitats and venturing out of it. So all these are possibilities with this human research program. I would just like to close with this quote from astronaut Michael Collins, saying that it's human nature to stretch, to go, to see, to understand. Exploration is not a choice really, it's an imperative. Thank you.